The moon is trying to kill you, your spacesuit is failing, your radiation alarm is screaming, and you're 200,000 kilometers from the nearest hospital. This isn't a horror movie, this is just a Tuesday on the moon. Every single second you're there, it's attacking you in a dozen different ways. And here is a question. If you could bring only one item to the moon to help you survive, what would it be? Comment down below. I'll pin the most creative answer. Now let's begin. When NASA announced the Artemis program, the world celebrated. Humanity was going back to the moon, not just for a quick visit like Apollo, but to stay, to build bases, to live there. Politicians gave speeches, engineers drew up blueprints, children dreamed of becoming lunar astronauts. But here's what they didn't tell you in those glossy press releases and inspiring videos. The moon is trying to kill us, and it's far better at it than we ever imagined. I'm not talking about science fiction. I'm not exaggerating for effect. I'm talking about real data from real missions gathered by real scientists who are genuinely worried about what they've discovered. See, we've learned more about the moon in the past decade than we did during the entire Apollo era, and what we've learned should make us think very carefully about rushing back. Let's start with something that sounds almost innocent. Dust. Just dust, right? How dangerous could that be? Well, imagine taking broken glass, grinding it down to a powder finer than talcum, giving it an electric charge so it sticks to absolutely everything, and then spreading it across an entire world. That's lunar dust, and it's one of the most insidious threats we've ever encountered in space exploration. The Apollo astronauts noticed this immediately. Eugene Cernan, commander of Apollo 17, said the dust was one of the most aggravating, restricting things they dealt with. It got into everything: their equipment, their spacesuits, their spacecraft. When they brought it back inside the lunar module, it floated in the air, and they breathed it in. Several astronauts reported what they called lunar hay fever. Sneezing, nasal congestion, irritated sinuses. One Apollo flight surgeon documented something even more concerning. The symptoms got worse with each exposure, and blood tests showed increased eosinophils, a type of white blood cell that responds to allergic reactions. Here's the truly frightening part. The Apollo missions lasted only a few days on the lunar surface. A handful of moonwalks, limited exposure, but Artemis missions are planned to last weeks, eventually months. Astronauts will be conducting dozens of extravehicular activities, walking through dust storms they create with every step. And we still don't fully understand what prolonged exposure to lunar dust does to human lungs. NASA scientists at Johnson Space Center have been studying this problem intensely. They've created detailed simulations of lunar dust using pulverized basalt. When you touch this simulated dust, it clings to your skin like nothing you've ever felt on Earth. It's unnaturally adhesive. You can shake your hand, brush it off, and it just stays there. Now imagine that getting into your lungs day after day, week after week. The problem isn't just irritation. Lunar dust particles are incredibly sharp. They haven't been worn smooth by wind and water like Earth dust because the moon has no atmosphere. Billions of years of micrometeorite impacts have shattered the lunar surface into razor-sharp fragments at the microscopic level. When you breathe these particles in, they're like tiny pieces of glass scraping the inside of your lungs. In the mining industry on Earth, we've known for over a century what happens when people breathe in rock dust for years. Black lung disease, silicosis, permanent scarring, cancer. And that's with Earth dust, which is far less sharp and abrasive than lunar regolith. But it gets worse. Remember how I mentioned the dust is electrically charged? The sun constantly bombards the moon with energetic particles. These particles charge up the dust grains, creating static electricity. This is why lunar dust doesn't just sit on the surface. It levitates, it floats, it gets kicked up by the slightest disturbance and hangs in the vacuum, drifting into every crack, every seal, every opening. Apollo astronauts found dust in sealed containers. It got through zippers. It penetrated layers of protection they thought were airtight. NASA engineer Amy Fritz, who works in what they call the dirty labs at Johnson Space Center, has spent years trying to solve this problem. She and her team have tested hundreds of solutions: electric force field shields, special coatings, ultrasonic vibrations. Nothing works perfectly. The dust is just too clingy, too pervasive, too insidious. In a 2026 interview, she described it as one of the most fundamental challenges they face. Not rocket science, not propulsion, dust. Think about what this means for a lunar base. Every time astronauts come back inside after a moonwalk, they bring dust with them. It contaminates the habitat, it gets into the life support systems, it clogs filters, it damages equipment. Apollo astronauts reported that the smell of lunar dust reminded them of gunpowder or wet ashes. That smell came from the dust reacting with the moisture in the air. What does that tell you? It's chemically reactive. It's not just sitting there inert. It's doing something. And here's something that should really make you pause. We don't have good long-term data on what lunar dust exposure does to human health. The Apollo astronauts who walked on the moon are now in their 80s and 90s. Some have passed away. Scientists have tried to study their medical records, looking for patterns, but the sample size is tiny. Only 12 humans have ever walked on the moon. 12. That's not enough to draw solid conclusions about long-term health effects. We're essentially planning to send people to live in an environment where we don't fully understand one of the primary hazards they'll face daily. If you're enjoying this deep dive into the real challenges of lunar exploration, do me a favor and give this video a like. It really helps the channel grow and lets me know you want more content like this. Now let's talk about something even more dangerous than the dust: radiation, but not the kind you might be thinking of. We all know space has radiation, cosmic rays, solar wind. That's basic astronomy. What most people don't realize is that the moon has no magnetic field to protect you. Earth's magnetic field acts like a giant shield, deflecting most of the dangerous charged particles streaming through space. Stand on the moon and you're naked to the cosmos. NASA scientists have been studying this problem extensively for the Artemis program. The data is genuinely concerning. During a typical day on the lunar surface, an astronaut receives about the same radiation dose that someone on Earth gets in an entire year. That's just on a normal day. A quiet day. But the sun isn't always quiet. In August of 1972, one of the largest solar storms of the 20th century erupted. Massive solar flares, huge clouds of energetic particles racing through space at nearly the speed of light. It happened right between the Apollo 16 and Apollo 17 missions. If astronauts had been on the moon during that storm, they would have been exposed to potentially lethal doses of radiation. Some scientists estimate it could have been enough to cause acute radiation sickness. Others think it might have been fatal. That was pure luck. Timing, a roll of the cosmic dice that happened to land in humanity's favor. We weren't there when the sun decided to throw a tantrum. But here's the thing about the sun. It goes through 11-year cycles of activity. Right now, in 2026, we're approaching what's called solar maximum, the most active phase of the cycle, the time when massive solar storms are most likely to occur. And that's exactly when we're planning to send astronauts back to the moon for extended stays. Dr. Ian Richardson, a scientist at NASA's Goddard Space Flight Center, has been studying space weather for decades. He remembers the 1972 event clearly. He was a kid in England when it happened, and the solar activity was so intense it disrupted television signals across the country. The BBC had to tell people that the interference wasn't due to faulty equipment. It was the sun. Today, Richardson works on forecasting these events, trying to predict when the sun will unleash its fury. But here's the problem. Even with all our advanced satellites and monitoring systems, we typically get only about 18 to 24 hours of warning before a major solar storm hits. 18 hours. That's how much time astronauts on the Moon would have to take shelter when sensors detect a massive solar eruption heading their way. It sounds like a lot of time, doesn't it? But think about what that means in practice. You're out on the surface, exploring a crater 50 kilometers from your base. You get the warning, you have to stop what you're doing, get back to your rover, drive back to the habitat, get inside, and hunker down in a specially shielded area, and hope that the forecasters were right. Hope that the storm is coming from where they think it is. Hope that your shielding is enough, because if you're wrong, if you miscalculate, if you're caught outside when one of these solar particle events hits, the consequences are severe. The radiation would penetrate your spacesuit. It would damage your DNA, increase your cancer risk dramatically, in the worst cases cause acute radiation sickness right there on the lunar surface. Nausea, vomiting, confusion, and there's no hospital on the Moon, no emergency room, no oncology department. You're 3 days away from Earth at minimum. 3 days in a spacecraft getting sicker while Mission Control tries to figure out what to do. The University of Michigan runs something called the CLEAR Center, which stands for Center for All Clear SEP Forecast. SEP means Solar Energetic Particles. Their entire job is to predict these deadly storms and figure out how to keep astronauts safe. The researchers there have studied hundreds of solar events, building models, analyzing patterns, trying to find ways to give astronauts more warning time. But the sun doesn't follow a script. It's chaotic, unpredictable. Sometimes it throws massive eruptions with barely any warning at all. In November of 2024, a team of scientists published a comprehensive study in the journal Space Weather. They analyzed 262 large historical solar particle events and calculated what the radiation dose would be for astronauts on the Moon under different shielding scenarios. The results were sobering. Even with substantial aluminum shielding, a single major solar storm could deliver enough radiation to exceed an astronaut's recommended annual limit. In some scenarios, one storm could exceed their entire career limit. Let me put that in perspective. NASA sets strict limits on how much radiation astronauts can be exposed to over their lifetime. These limits are designed to keep the risk of cancer and other health problems within acceptable levels. One bad solar storm on the Moon could end an astronaut's career. Just like that. One event. And we can't predict with certainty when these events will happen or how severe they'll be. But solar storms aren't even the biggest radiation problem. There's something worse. Something that never stops. Galactic cosmic rays. These are high-energy particles that come from exploding stars, supernovae that died millions of years ago in distant galaxies. They've been accelerating through space for eons, moving at nearly the speed of light. When they hit atoms, they create cascades of secondary particles, neutrons, gamma rays. These particles can pass right through spacecraft walls, through habitats, through human bodies. On Earth, we're protected. The atmosphere and the magnetic field block most of this radiation. On the International Space Station, astronauts are still partially protected by Earth's magnetic field. But on the Moon, there's nothing between you and the galaxy. A Nature astronomy study published in July of 2024 used something called the Red Moon model, which stands for Radiation Environment and Dose on the Moon. They calculated that the radiation exposure on the lunar surface from galactic cosmic rays alone is about 66% of what you'd get in interplanetary space. That's better than being in a spacecraft in deep space, but not by much. Here's where it gets really interesting, and by interesting I mean terrifying. You might think, well, we'll just build underground. dig into the lunar regolith, use the moon itself as a shield. That should work, right? And you'd be partially correct. The study found that as you go deeper underground, the radiation from cosmic rays does decrease. But here's the twist. At shallow depths, just below the surface, the radiation can actually increase slightly before it starts dropping. Why? Because when cosmic rays hit the lunar soil, they create those secondary particles I mentioned. At certain depths, you're getting hit by both the original cosmic rays penetrating down and the secondary particles being created in the material around you. You need to go deep. About 3 meters underground before the shielding becomes really effective. 3 meters of lunar regolith. That's roughly 10 feet. Now think about what that means logistically. You're not just landing on the moon and setting up a habitat. You're excavating, moving massive amounts of material, building underground, all while wearing a spacesuit, dealing with that razor-sharp dust and racing against radiation exposure. It's an engineering challenge of staggering proportions, and even if you build that perfect underground base, you still have to go outside. The whole point of being on the moon is to explore it, to conduct science, to mine resources. To prepare for missions to Mars, you can't do that from a bunker. So astronauts will have to venture out, exposing themselves to radiation with every excursion. Mission planners have to calculate carefully how many hours outside per week, how many days total on the surface before an astronaut reaches their exposure limit. It's like having a countdown clock on human activity. Speaking of Mars, if you found this information fascinating and terrifying, you absolutely need to check out my video called Why the First Humans on Mars Will Never Come Back. It explores similar themes, but on an even more extreme scale. The challenges we face on the moon are just a preview of what awaits us on the red planet. The link is in the description, but let's get back to the moon because we're not done with the dangers yet, not even close. Remember those micrometeorites I mentioned earlier? The ones that have been pulverizing the lunar surface for billions of years, creating all that sharp dust? Well, they're still falling, constantly, every single day, and they don't burn up in an atmosphere like they do on Earth, because the moon doesn't have one. They just slam straight into the surface at speeds of up to 70 kilometers per second. That's over 156,000 miles per hour. Now, most of these micrometeorites are tiny, smaller than a grain of sand, but at those speeds, even a tiny particle carries enormous kinetic energy. It's like being shot with a microscopic bullet, and they're falling all the time. A 2025 study published on Archive analyzed micrometeoroid impact rates for an Artemis-era lunar base. They used NASA's Meteoroid Engineering Model 3, which is the best simulation we have of the meteoroid environment in space. Their findings? A lunar base the size of the International Space Station, roughly 100 meters by 100 meters by 10 meters, would experience between 15,000 and 23,000 micrometeoroid impacts per year. Let that sink in. 15 to 23,000 tiny projectiles slamming into your base every single year. That's 40 to 60 impact every single day, and the impact rate varies depending on where you are on the moon. The poles experience fewer impacts, which is one reason NASA is interested in building near the South Pole. But even there, you're still talking about thousands of strikes annually. Now, before you panic completely, modern shielding technology is actually pretty good at handling these impacts. Something called Whipple shields, named after astronomer Fred Whipple, use multiple layers of material spaced apart. When a micrometeoroid hits the outer layer, it vaporizes into a cloud of plasma. That cloud spreads out and hits the inner layers with much less concentrated energy. It's clever engineering. The same study found that state-of-the-art Whipple shields can protect against about 99.9997% of micrometeoroid impacts. But here's the thing, that protection only works for structures, for your habitat, your rovers. What about when you're outside in a spacesuit? Spacesuits can't have the same level of shielding. They have to be flexible. You have to be able to move. So when you're out on a moonwalk, you're essentially walking around in a radiation and micrometeoroid environment with minimal protection. The odds of getting hit by a dangerous particle on any single excursion are low, but they're not zero. And the more time you spend outside, the more that probability adds up. It's like playing Russian roulette with the universe. Most chambers are empty, but there's always that chance. And unlike Earth, where you can check the weather forecast and decide whether to go outside, on the Moon, you're always rolling the dice. Clear day? Doesn't matter. Still getting bombarded by cosmic rays, still at risk from micrometeorites, still breathing in that toxic dust. Let's talk about temperature for a moment, because the Moon isn't just dangerous from things hitting it or radiating through it. It's dangerous because of its extremes. During the lunar day, which lasts about 14 Earth days, surface temperatures can reach 127 degrees Celsius. That's 260 degrees Fahrenheit, hot enough to boil water, hot enough to cause severe burns instantly if your spacesuit failed. And then, during the lunar night, which also lasts 14 Earth days, temperatures plummet to minus 173 degrees Celsius. That's minus 280 degrees Fahrenheit. Cold enough to freeze carbon dioxide, cold enough to make metal brittle and shatter. Your habitat has to handle this temperature swing of 300 degrees. Your equipment has to function in these extremes. Your life support systems can't fail when it's either an oven or a freezer outside. And remember, there's no atmosphere to moderate these temperatures, no greenhouse effect, no weather patterns, just the sun beating down or the cold void of space pulling heat away. NASA engineers designing the Artemis habitats are keenly aware of these challenges. They've been testing materials in thermal vacuum chambers, subjecting them to temperature cycles that simulate lunar conditions. Some materials crack, others warp, seals fail, lubricants either melt or freeze solid. It's an unforgiving environment that punishes any weakness in design or manufacturing. And here's something most people don't think about. The boundary between sunlight and shadow on the Moon is razor sharp. No atmosphere means no diffusion of light. You can be standing with 1 foot in 127 degree sunlight and the other foot in minus 173 degree shadow. Your spacesuit has to handle both simultaneously. The thermal stress on materials in that situation is immense. But wait, there's more. The Moon is also electrically active in ways we didn't fully understand until recently. The charged particles from the Sun don't just charge up the dust, they create an entire plasma environment around the Moon. During certain parts of the lunar orbit, when the Moon passes through Earth's magnetotail, the electrical environment changes dramatically. Surfaces can accumulate charge, astronauts can accumulate charge, touch the wrong thing, and you could get a shock that damages sensitive electronics or, worse, disrupts your spacesuit systems. NASA conducted studies on this phenomenon, documented in technical reports from Marshall Space Flight Center. They found that during certain phases of the lunar month, the charging environment is severe enough that special precautions are necessary. Equipment needs to be grounded, astronauts need to discharge themselves before entering habitats. It's like living in a place where static electricity isn't just annoying, it's potentially deadly. Now let's talk about something that sounds almost science fiction but is absolutely real. The Moon rings like a bell. I know that sounds strange, but hear me out. When meteorites impact the lunar surface, or when there are internal stress releases, the Moon experiences what scientists call Moon Quakes. These aren't like earthquakes, they're different, weirder, and in some ways more unsettling. Apollo astronauts left seismometers on the lunar surface. These instruments recorded data for years, sending information back to Earth about the Moon's internal activity. What they discovered was fascinating and slightly disturbing. The Moon experiences several types of quakes, deep moon quakes, occurring hundreds of kilometers below the surface, thermal moon quakes caused by the extreme temperature changes between day and night, meteorite impact quakes, and shallow moon quakes. It's those shallow moon quakes that should concern anyone planning to build a permanent base. These quakes occur relatively close to the surface, maybe 20 to 30 kilometers down. They're not frequent, happening maybe once or twice a year. But when they do occur, they're surprisingly strong. Some have registered over 5 on the Richter scale. That's strong enough to damage structures, strong enough to crack foundations, strong enough to be dangerous if you're inside a habitat. But here's the really weird part. Remember how I said the moon rings like a bell? On Earth, when an earthquake happens, the shaking typically lasts for a minute or two at most. The ground shakes, then it stops. Energy dissipates through the Earth's layers. But on the moon, because it's cold and rigid inside, without the warm plastic layers that Earth has, moonquakes can continue for hours. The seismic waves just keep bouncing around inside the moon, reverberating, creating this prolonged shaking that goes on and on. Imagine being in a lunar habitat when a shallow moonquake strikes. The ground starts shaking. You're waiting for it to stop, like an earthquake would on Earth. But it doesn't stop. It keeps going. 10 minutes, 20 minutes, an hour, 2 hours. The whole time you're wondering if your habitat seals will hold, if dust is going to start leaking in through cracks, if your life support systems are going to fail. It's the kind of psychological stress that's hard to prepare for, and we don't fully understand the pattern of these quakes yet. The Apollo seismometers only operated for a few years. That's not enough time to characterize the full range of lunar seismic activity. We might be missing rare but severe events. We might not understand the triggers. Building a permanent base means accepting that we're constructing on a world whose internal activity is still largely mysterious to us. Let's shift gears and talk about something that affects every single aspect of living on the moon: the vacuum. Now you might think, well, we know space is a vacuum. We've dealt with that on space stations. What's the big deal? The big deal is that on a space station, you're in a sealed environment, a can floating in space. On the moon, you're living on a surface surrounded by vacuum. You're constantly interfacing with it, walking in it, building in it. And vacuum does strange things. For one thing, materials behave differently in vacuum. On Earth, there's always a thin layer of water molecules and oxygen on surfaces. And this prevents certain types of chemical bonding. But in the vacuum of space, when two clean metal surfaces touch, they can cold weld, literally fuse together at the atomic level. This phenomenon, called vacuum welding or cold welding, has caused problems on spacecraft before. Moving parts seize up, mechanisms jam. Imagine a rover wheel suddenly welding itself to its axle, or a hatch that won't open because the metal surfaces have bonded. NASA engineers have to account for this by using special coatings and lubricants, but those solutions have their own problems. Remember those temperature extremes? Lubricants that work at 127 degrees might not work at -173. Finding materials that function across that range in vacuum while being resistant to radiation and abrasive dust is extraordinarily difficult. There's also the problem of outgassing. Many materials release trapped gases when exposed to vacuum: plastics, adhesives, certain metals. These gases can contaminate surfaces, interfere with instruments, even create thin atmospheres inside enclosed spaces that you don't want. Apollo astronauts reported strange smells and observations that scientists later attributed to outgassing. Every material used in a lunar habitat has to be tested extensively to ensure it won't release harmful substances in the vacuum environment. And here's something that combines multiple dangers in a particularly nasty way. The moon has no atmosphere to burn up small meteoroids, as we discussed, but it also has no atmosphere to slow down ejecta. When a meteoroid hits the lunar surface, it creates an explosion. Material gets thrown up at high velocity. On Earth, that material would be slowed by air resistance and fall back down relatively close to the impact site. On the Moon, that ejector can travel for kilometers in ballistic arcs, maintaining high velocity the entire way. This creates a phenomenon called secondary impacts. A meteorite hits somewhere over the horizon, and suddenly you're being pelted with high-velocity rock fragments. Studies conducted by NASA researchers at Marshall Space Flight Center found that these secondary ejector impacts could pose significant risks to surface operations. A single large meteorite impact could create a shotgun blast of debris spreading across vast areas, and you might have no warning. The primary impact could happen on the far side of the Moon, completely invisible to you, and minutes later you're being hit by the consequences. Think about what this means for surface activities. You're out exploring, collecting samples, setting up experiments. Suddenly, without any warning, rocks start raining down around you, not gently, falling, slamming into the surface at hundreds or thousands of meters per second. Your spacesuit might protect you from small pieces, but larger fragments could puncture it. And unlike in the movies, a punctured spacesuit in vacuum is an immediate, life-threatening emergency. Now let's talk about something that doesn't get discussed much in public NASA presentations: the psychological challenges of living on the Moon. We've talked about physical dangers, but the mental health aspects are equally concerning. The Moon is a desolate, grey, lifeless place. There's no weather. No clouds, no rain, no wind. The only changes are the slow march of shadows as the sun moves across the sky and the Earth hanging there, going through its phases. Astronauts on the International Space Station at least get to see Earth in all its glory. Blue oceans, green continents, white clouds. It's a constant reminder of home, of life, of everything they're temporarily away from. But on the Moon, Earth is smaller, more distant. You can see it, yes, but it's not the same. You're standing on a dead world, surrounded by nothing but grey dust and black sky, and home is 250,000 miles away. The isolation would be profound. Communication delays, while not as bad as Mars, still exist. It takes over a second for radio signals to travel between Earth and Moon. That doesn't sound like much, but it makes real-time conversation impossible. Every exchange has this awkward pause. Ask a question, wait, get an answer, wait. It's unsettling, unnatural. Human conversation doesn't work that way, and if something goes wrong, if there's an emergency, you can't just come home. The launch window, the trajectory, the life support calculations, all of that has to be planned. Even in the best-case scenario, you're days away from Earth, days away from help, days away from medical facilities, from family, from everything familiar. The psychological pressure of knowing that if something goes seriously wrong, you're essentially on your own would be immense. Studies of Antarctic research stations and other isolated environments have shown that humans struggle with prolonged isolation, even when they're still on Earth. Depression, anxiety, interpersonal conflicts, cabin fever. Now amplify that by putting people in a place where they can't go outside without a spacesuit, where the environment is actively trying to kill them, where one mistake, one equipment failure, one moment of carelessness could be fatal. The mental health challenges would be unprecedented. NASA does screen astronauts for psychological resilience. They conduct training in isolated environments. They prepare crews for the realities of space. But there's a difference between simulation and reality. There's a difference between knowing intellectually that you're on the Moon and actually being there, actually living with the constant low-level stress of a hostile environment. And here's something that might be the most insidious danger of all. It's something scientists call the normalization of deviance. It's what happens when you do something risky repeatedly without consequence, and it starts to feel normal. You start to take shortcuts, get complacent. We've done this procedure 100 times and nothing bad happened, so maybe we don't need to follow every step exactly. This psychological phenomenon has been implicated in numerous disasters, including the Challenger and Columbia Space Shuttle accidents. On the Moon, where danger is constant but often invisible, the risk of normalization would be high. That radiation detector showing elevated levels? You've seen it high before and nothing happened. Maybe you can extend your surface excursion by an hour. That dust seal that's not quite perfect? It's been like that for weeks and the habitat pressure is holding. Maybe you don't need to replace it right away. Those small decisions accumulated over time could lead to catastrophic failures. The Apollo missions were short enough that crews maintained peak alertness the entire time. Everything was new. Everything was dangerous. But on a long-duration mission measured in months rather than days, maintaining that level of vigilance would be psychologically exhausting. Human nature is to adapt, to become comfortable. On the Moon, comfort could be deadly. Let's return to the radiation problem because there's an aspect we haven't fully explored yet. The biological effects. We know radiation damages DNA, we know it increases cancer risk, but there are other effects that are less well understood and potentially more immediately concerning. Radiation affects the central nervous system. High doses can impair cognitive function, decision-making, memory, reaction time. These aren't theoretical concerns. Studies of astronauts who've spent long periods in space, even in the relatively protected environment of the International Space Station, have shown measurable changes in brain structure and function. Now imagine those effects on the Moon, where radiation exposure is significantly higher. You need astronauts to be mentally sharp, making complex decisions, operating sophisticated equipment, responding to emergencies. But the environment they're working in is literally damaging their brains at the cellular level. It's a cruel irony. The very act of being on the Moon, doing the work that needs to be done, degrades your ability to do that work safely. There's also growing evidence that radiation affects the cardiovascular system. Studies of atomic bomb survivors and cancer patients who received radiation therapy have shown increased rates of heart disease and stroke years after exposure. Space radiation might have similar effects. An astronaut might complete a lunar mission, return to Earth apparently healthy, and then develop serious cardiovascular problems a decade later. We won't know the full scope of these long-term health effects until we actually send people to live on the Moon for extended periods. In other words, we're conducting an experiment on human health in real time, with astronauts as the test subjects. There's another radiation effect that's particularly concerning for long-duration missions: cataracts. Astronauts who've spent significant time in space have shown higher rates of cataract formation. The lens of the eye is particularly sensitive to radiation damage. On the Moon, with its higher radiation environment, this risk would be amplified. Imagine an astronaut 6 months into a year-long mission starting to develop vision problems, blurriness, difficulty seeing in low light. Those aren't minor inconveniences when you're operating complex machinery or navigating across unfamiliar terrain. And here's something that keeps medical researchers up at night. We don't really know how the human immune system will respond to the combined stresses of the lunar environment: radiation exposure, isolation, disrupted sleep cycles due to the strange day-night rhythm, constant low-level stress. Each of these factors individually can suppress immune function. Together, the effect might be synergistic, meaning the combined impact is worse than the sum of individual effects. Studies on the International Space Station have documented something called spaceflight-associated immune system dysregulation. Astronauts' immune systems don't work as well in space. They're more susceptible to infections. Latent viruses that have been dormant in their bodies can reactivate. Things like herpes simplex, varicella zoster, the virus that causes chickenpox and shingles. These viruses are present in most people's bodies, kept in check by a healthy immune system. But in space, with a weakened immune response, they can wake up. On a lunar base, far from advanced medical facilities, an immune-compromised crew would be particularly vulnerable. A simple infection that would be minor on Earth could become serious. And there's limited ability to evacuate someone for medical treatment. You can't call an ambulance. You can't rush someone to the hospital. You have to stabilize them, prepare a spacecraft, calculate a return trajectory, launch, and then endure a 3-day journey back to Earth. During all of that time, the patient's condition could be deteriorating. NASA has protocols for medical emergencies in space, of course. Astronauts receive medical training, they have medical supplies and equipment. But there are limits to what can be done in a small habitat with limited resources. You can't perform major surgery in a lunar base. You don't have the facilities, the equipment, the staff. Complex medical problems would require evacuation, and some conditions might deteriorate too quickly for that to be viable. Let's talk about something else that makes the Moon uniquely challenging: the lack of resources. On Earth, even in the most remote locations, there's air to breathe, water to drink if you can find it and purify it, materials to build with. The Moon has none of that readily available. The atmosphere, if you can even call it that, is so tenuous, it's effectively a vacuum. There's no liquid water on the surface. Everything you need to survive has to be brought from Earth or manufactured from lunar materials through complex processes. NASA talks a lot about in situ resource utilization, which is a fancy term for living off the land. The idea is that you'll extract water from ice deposits at the poles, break it down into hydrogen and oxygen for rocket fuel, and breathing air, use lunar regolith to make building materials, maybe even grow food in greenhouses. It sounds great in theory, but the reality is far more complicated. Those ice deposits at the lunar poles, they're in permanently shadowed craters. Places where the sun has never shone for billions of years. The temperatures there are among the coldest in the solar system. Minus 230 degrees Celsius. Minus 382 degrees Fahrenheit. That's colder than Pluto. Mining ice in those conditions would be extraordinarily difficult. Your equipment has to function in darkness and extreme cold. The ice is mixed with regolith. You have to extract it, separate it, purify it. Every step is an engineering challenge. And the quantities might not be as abundant as we hope. Orbital measurements suggest there's water ice at the poles, yes, but the exact amounts and concentrations are uncertain. You might drill or excavate and find less than expected. Or it might be distributed in ways that make extraction inefficient. We won't really know until we get there and start trying to use it. Building a lunar base that depends on local water resources means gambling that those resources exist in sufficient quantities and accessible forms. The same goes for making building materials from lunar regolith. Yes, you can theoretically melt regolith and form it into bricks or structures, but that requires enormous amounts of energy. Where does that energy come from? Solar panels work during the lunar day, but remember, the lunar night lasts 14 Earth days, 2 weeks of darkness. You need energy storage systems that can keep your base running for 2 weeks without sunlight. Batteries, how many would you need, and how much would they weigh to transport from Earth? Some proposals suggest using nuclear reactors for continuous power. That solves the energy problem, but introduces new ones. Nuclear reactors are complex, heavy, and require careful handling. A malfunction in a lunar nuclear reactor would be catastrophic. There's no evacuation for hundreds of miles. No hazmat team, no containment specialists. The crew would have to deal with it themselves or abandon the base. There's also the challenge of food production. Bringing all food from Earth is possible, but expensive and limiting. Growing food on the Moon sounds appealing. Greenhouses utilizing hydroponic systems, LED lighting, maybe even some of that extracted lunar water. But plants need more than just water and light. They need nutrients, a growing medium, a controlled atmosphere. Protection from radiation, the greenhouses would have to be shielded, which means more mass to transport or excavate. And here's a biological problem that doesn't get discussed much. We don't fully know how plants will grow in 1/6 gravity. Most of our experience with space agriculture comes from the International Space Station, which is in microgravity. Some experiments have been done and plants can grow, but their behavior is different. Root systems develop differently. Water distribution in soil works differently. Scaling that up to provide meaningful amounts of food for a lunar crew is uncharted territory. Then there's the psychological benefit of growing things. Studies have shown that plants have significant mental health benefits for people in isolated environments. The smell of earth, the sight of green leaves, the act of tending to living things. It's grounding, literally and figuratively. But maintaining a garden in a hostile, sterile environment requires constant effort and resources. If the greenhouse fails, you lose not just a food source, but a psychological lifeline. Speaking of psychological factors, let's talk about the view. This might sound trivial compared to radiation and micrometeorites, but it's important. On Earth, we're surrounded by a complex, ever-changing environment. Weather patterns, clouds moving, trees swaying, birds flying. Even in the most barren desert, there's wind, there's variation, there's life of some kind. The human brain evolved in this rich, sensory environment. The moon offers none of that. It's static, unchanging, the same grey regolith stretching to the horizon, the same black sky, the same stars which don't twinkle because there's no atmosphere. The only motion is the slow arc of the sun and the phases of Earth. Some people might find that stark beauty appealing for a while, but weeks, months, the sensory deprivation could be profound. Experiments in isolated environments on Earth have shown that humans need stimulation, variety, change. When deprived of those things, people can develop what's sometimes called prison psychosis or cabin fever, irritability, depression, difficulty concentrating, paranoia in extreme cases. And those studies were done on Earth, where at least there's gravity and weather and some variation in the environment. The moon would be even more monotonous. NASA is aware of these issues. They're working on habitat designs that include varied lighting, colored walls, virtual windows, showing scenes from Earth. But there's a difference between a video of a forest and actually being in a forest, between a picture of the ocean and hearing waves crash. The human sensory system can detect the difference between real and simulated environments. Whether those simulations will be sufficient for long-term mental health is an open question. Now let's discuss something that ties many of these dangers together: the concept of cascading failures. In a complex system like a lunar base, different systems are interconnected. Life support, power generation, communication, thermal control, each depends on the others. If one system fails, it can trigger failures in other systems, creating a cascade that rapidly spirals out of control. Imagine this scenario: a solar storm damages some of the solar panels on your habitat. Power generation drops. To conserve energy, you have to reduce heating. Temperature inside the habitat starts to drop. As it gets colder, some electronic systems start malfunctioning. They weren't designed to operate at these lower temperatures. One of the systems that fails is part of the life support monitoring. Now, you can't accurately track oxygen levels. You adjust manually, but without good data, you're guessing. You set the oxygen generation slightly too low to be extra cautious about not wasting power. Over time, oxygen levels drift downward. Crew members start feeling fatigued, which they attribute to stress and overwork. Their decision-making becomes impaired. They make a mistake while trying to repair the solar panels. More damage occurs. This kind of cascade can happen faster than you might think. And in an environment where every system is critical, where there's no margin for error, it's a nightmare scenario. Engineers design redundancy into spacecraft and habitats precisely to prevent this. Backup systems, fail-safes, multiple layers of protection. But every backup system adds mass, complexity, and cost. There's always a balance between safety and practicality. And sometimes, in the real world, that balance is wrong. The Apollo 13 mission is the classic example of how quickly things can go wrong in space and how close to disaster even a successful recovery can be. An oxygen tank exploded due to a combination of design flaws and procedural mistakes. Suddenly the crew was in a crippled spacecraft with limited power, limited water, limited air. They survived through a combination of brilliant engineering, quick thinking, and frankly, luck. They were close enough to Earth that a return trajectory was feasible. They had just enough resources to make it. On the Moon, in a surface habitat, some of those options wouldn't exist. You can't abort to Earth immediately. You're stuck there until a launch window opens and a spacecraft is ready. If your habitat is failing, your options are limited. You could try to move to a backup shelter if one exists. You could attempt repairs, but some failures might be unrecoverable. Some situations might be unsurvivable. And here's something that makes this even more terrifying. The Moon is not a place where you can just improvise solutions from available materials like they did in Apollo 13. On that mission, engineers on the ground figured out how to adapt carbon dioxide scrubbers using materials available on the spacecraft: duct tape, plastic bags, cardboard. It was ingenious improvisation. But on the Moon, you don't have random materials lying around. Everything has a specific purpose. Every gram of mass was carefully chosen and transported at enormous cost. There's no junkyard to rummage through, no hardware store. If you need something you don't have, you're out of luck. This limitation extends to every aspect of lunar operations. Medical supplies? You have what you brought. Run out of a critical medication and you can't get more until the next resupply mission, which might be months away. Equipment breaks? You can only fix it if you have the right spare parts. Manufacturing capability is limited. 3D printing might help with some components, but you need the right materials and the right designs. You can't print complex electronics or specialized materials. There's also a fundamental challenge with the lunar environment that affects everything. The dust, which we talked about earlier, doesn't just damage equipment and threaten health, it also interferes with solar panels. Those panels are critical for power generation, but lunar dust settles on them, reducing their efficiency. During a moonwalk, dust gets kicked up and can coat solar panels. Over time, the accumulated dust significantly reduces power output. On Earth, rain washes dust off solar panels, wind blows it away. On the Moon, there's no rain, no wind. The dust just sits there. And remember, it's electrostatically charged, so it clings stubbornly. Cleaning solar panels might sound simple, but it's another task that requires extravehicular activity, which means radiation exposure, which means using up part of your lifetime dose allowance. Every task outside has a cost measured in health risk. Some engineers have proposed using mechanical wipers or electrostatic systems to repel dust from solar panels. But these systems add complexity, mass, and potential failure points. And in the abrasive lunar environment, mechanical systems wear out. Wipers might become coated with dust themselves, turning into abrasive pads that scratch the solar panels they're supposed to clean. It's a problem with no perfect solution. Let's talk about communication, because even that becomes a challenge on the Moon. From Earth, we can only communicate with the near side of the Moon, the side facing us. If you're on the far side, you're out of direct contact. You need relay satellites to maintain communication. NASA plans to establish a network of satellites around the Moon for continuous coverage, but that's another complex system that has to work flawlessly. If those satellites fail, portions of the Moon become communication dead zones. And even on the near side, communication isn't always straightforward. The Moon's surface is rough, with mountains, crater walls, and ridges that can block line-of-sight signals. If you're in a deep crater or on the far side of a mountain from your base, you might lose contact. This makes exploration risky. You venture out to investigate something interesting, go over a ridge, and suddenly you're cut off. If something goes wrong, if you have an emergency, no one knows. You're alone in the truest sense of the word. This isolation during surface excursions is profoundly different from any exploration on Earth. Even in the most remote locations on our planet, there's usually some way to signal for help. Satellite phones, emergency beacons. And even if technology fails, there's an atmosphere that carries sound, so you could potentially shout and be heard. On the Moon, sound doesn't travel through vacuum. Radio is your only option. If your radio fails or you're in a dead zone, you're in serious trouble. NASA protocols would require astronauts to work in pairs during moonwalks, which provides some safety. But it also means that if something goes wrong, both people are at risk. If one person has a medical emergency, the other has to help while also ensuring their own safety. It's a different calculus than rescue operations on Earth, where help can come from outside the danger zone. Now let's address something that's often glossed over in discussions of lunar colonization: the economic reality. Building a base on the Moon is staggeringly expensive. Estimates vary, but we're talking about hundreds of billions of dollars at minimum. Every kilogram of mass you send to the Moon costs tens of thousands of dollars. A single habitat module could cost more than the entire budget of some countries. This economic pressure creates dangerous incentives. There's pressure to cut costs, to make systems lighter, to reduce redundancy. Every backup system you eliminate saves mass and money, but it also reduces safety margins. The history of spaceflight includes numerous examples of cost pressures leading to compromises that later contributed to disasters. The Space Shuttle program famously had safety features reduced or eliminated during development to save money. Those decisions eventually proved fatal. With lunar bases, the same pressures will exist. Corporations and governments funding these missions will want results, will want to demonstrate progress, will want to justify the enormous expenditures. That creates pressure to push forward, even when safety concerns haven't been fully addressed, to launch on schedule even when testing is incomplete, to extend missions beyond their designed parameters because bringing people home and sending new crews is expensive. And here's a question that doesn't get asked enough. What happens if someone dies on the Moon? Not an if, really, but when. Space exploration is dangerous. People have died in the pursuit of it. The Apollo 1 fire killed 3 astronauts during a ground test. The Challenger and Columbia disasters killed 14 more. The Soviet and Russian space programs have had their own tragedies. It's a dangerous business, and everyone involved knows the risks. But those deaths occurred either on the ground or in low Earth orbit, relatively close to home. A death on the Moon would be different. The body couldn't be returned immediately. It would have to be stored, preserved somehow, until a return mission was available. The psychological impact on the surviving crew members would be immense. They'd have to continue their mission, continue working, while dealing with the grief and trauma. And they'd be acutely aware that they're in the same environment that killed their colleague. There's also the question of what happens to the body long term. Do you bring it back to Earth? That takes up mass that could be used for other cargo. Do you bury it on the Moon? That raises questions about contamination, about respect for the deceased, about what future generations will think. These aren't just practical questions, they're deeply human, emotional, ethical questions that don't have easy answers. The International Space Station has protocols for what to do if a crew member dies, including temporary preservation methods. But those protocols assume a relatively quick return to Earth is possible. On the Moon, especially as missions get longer and base is more permanent, the situation is more complex. You might not have an immediate return option. you might have to live and work alongside the physical reminder of how dangerous your environment is. Let's talk about something else that makes the Moon uniquely hazardous: time. The Apollo missions were short-term affairs, a few days on the surface at most. Equipment only had to function for a limited period. But permanent or semi-permanent bases mean equipment that has to work for months or years in the harsh lunar environment. And that environment is brutal on materials. The temperature cycling alone causes metal fatigue. Materials expand when heated, contract when cooled. Do that enough times and microscopic cracks develop. Those cracks grow. Eventually, structural failures occur. The vacuum accelerates degradation of many materials. Radiation causes chemical changes in plastics and composites, making them brittle. The dust abrades surfaces, wearing away coatings and protective layers. NASA engineers designing lunar base components have to account for all of this. They run accelerated aging tests, exposing materials to temperature cycles, radiation, and simulated lunar dust to see how they hold up. But there's only so much you can simulate in a lab on Earth. The real lunar environment is the ultimate test, and we won't know how well things hold up until they've been there for extended periods. This creates a maintenance nightmare. Systems that would last decades on Earth might only last months on the Moon. Constant repairs and replacements become necessary, but every repair requires human intervention, which means more extravehicular activities, more radiation exposure, more opportunities for something to go wrong. It's a vicious cycle. The harsh environment requires more maintenance, which exposes people to the harsh environment, which increases health risks. And here's a particularly insidious problem. Reliability testing on Earth can tell you how likely something is to fail, but it can't predict the exact moment of failure. A component might be rated for 10,000 hours of operation with a 99% confidence interval, but that means there's a 1% chance it fails earlier. When you have hundreds or thousands of components in a lunar base, each with its own failure probability, the math starts working against you. The chances that something somewhere will fail at an inconvenient time become disturbingly high. This is why aerospace engineers talk about mean time between failures and redundancy. You design systems so that when one component fails, there's a backup. But backups add mass, cost, and complexity, and backups can fail too. There's a balance between reliability and practicality, and finding that balance for lunar bases is incredibly difficult. Consider a simple example: a pump in the water recycling system. On Earth, if a pump fails, it's annoying but manageable. You call a plumber. On the Moon, a failed pump in the life support system could be catastrophic if there's no backup. Water is precious. You can't just use stored water indefinitely while you wait for a replacement pump to arrive from Earth. So you install a backup pump, but now you have two pumps to maintain, two potential failure points. And if both fail, you're in serious trouble. Engineers deal with this by designing systems with multiple levels of redundancy and by carrying extensive spare parts. But there are limits. You can't bring spares for every single component. You have to make risk-based decisions about what's most likely to fail and what's most critical. Sometimes you guess wrong. Sometimes the thing that fails is something you didn't adequately prepare for, and on the Moon, being unprepared can be deadly. Now let's discuss something that connects to the very reason we want to go to the Moon in the first place: science and exploration. The Moon is scientifically fascinating. Its ancient surface holds clues to the early solar system. The far side is one of the best places in the solar system for certain types of astronomy because it's shielded from Earth's radio emissions. The geological diversity, especially at the poles, offers incredible research opportunities, but conducting that science requires people to go out and do it, to set up experiments, to collect samples, to explore. And every moment spent doing science is a moment exposed to all the dangers we've discussed. It's a tragic paradox. The very activities that justify the enormous cost and risk of going to the moon are activities that increase the risk to human life. Remote robots can do some of this work, of course, and in many cases they're better suited for it. Robots don't need life support, don't get tired, don't worry about radiation exposure. NASA's robotic missions to the moon have returned incredible data. China's Chang'e missions, India's Chandrayaan program, these robotic explorers have taught us so much. The question becomes, do we really need humans on the moon, or are we sending them because of cultural and political reasons rather than scientific necessity? This is a debate that happens in the space science community, though not always publicly. Some scientists argue that humans are essential for exploration. We're adaptable, creative, can make decisions on the spot in ways that robots can't. Others point out that for the cost of sending one human mission, you could send dozens of robots. And robots don't come home in caskets. The truth is, probably somewhere in between. There are things humans can do better than robots, especially with current technology, but the margin is narrowing as artificial intelligence and robotics improve. In another decade or two, we might have robots capable of doing most of what humans can do on the lunar surface, without the enormous overhead of life support and safety systems. But assuming we do commit to human presence on the moon, let's talk about another challenge that's often overlooked: navigation. On Earth, we have GPS, satellites that precisely tell us where we are. We have landmarks, trees, buildings, roads. The sun and stars move in predictable patterns across the sky. Even in a desert or on the open ocean, there are ways to orient yourself. The moon is different. There's no GPS system, though NASA plans to establish one eventually. Landmarks exist, but the lack of atmosphere means no atmospheric scattering of light. That creates extremely harsh shadows and makes judging distances very difficult. Things that are far away can look close and vice versa. Astronauts on Apollo missions frequently misjudged distances. They'd see a boulder and think it was a short walk away, then discover it was actually kilometers distant. This distance distortion happens because our brains use atmospheric haze as a cue for distance. Objects that are far away look slightly hazy on Earth due to atmospheric scattering. On the moon, something kilometers away looks just as sharp and clear as something meters away. Your brain has no way to judge how far it is based on visual clarity. You have to rely on other cues, which are often misleading. The terrain itself compounds this problem. The moon is covered in craters of all sizes. From orbit or from a distance, the surface looks relatively smooth. But once you're on the ground, the landscape is chaotic. Small craters everywhere, rocks, ridges. It's like trying to navigate across a battlefield pockmarked with shell holes. Finding efficient paths is difficult, and every detour, every extra meter you have to travel costs time and consumables. Getting lost on the moon isn't like getting lost on Earth. There's no asking for directions, no calling for help if you're out of radio range, no trail of breadcrumbs to follow back. If your navigation equipment fails and you become disoriented, especially on the far side where Earth isn't visible in the sky as a reference point, you could wander until your life support runs out. It's a chilling prospect. NASA trains astronauts extensively in navigation using landmarks, sun angles, and instrument navigation. They'll have detailed maps created from orbital imagery, but maps can only show so much. The small-scale terrain features that you have to navigate around aren't visible from orbit. And if conditions change, if dust gets kicked up and reduces visibility, even good maps become less useful. Speaking of visibility, let's talk about dust in the air. Wait, you might say, there's no air on the moon, how can there be dust in the air? You're right, of course. But dust can still be suspended above the surface temporarily. When a rover drives by or when astronauts walk, they kick up dust. In Earth's atmosphere, that dust would quickly settle. On the moon, without air resistance, dust particles follow ballistic trajectories. They can arc high and take a long time to come back down. Some particles get electrostatically charged and can levitate above the surface for extended periods. During the Apollo missions, astronauts reported a phenomenon called horizon glow. Looking toward the horizon shortly before sunrise or after sunset, they saw a faint glow. Scientists believe this is sunlight scattering off electrostatically levitated dust particles. It's a beautiful phenomenon, but it also means there's a thin layer of suspended particles that could interfere with visibility and coat equipment. There's also been speculation about more dramatic dust phenomena. When meteorites impact the surface, they can create temporary clouds of dust and vapor. If a large enough impact occurs relatively nearby, it could create a hazardous environment for a brief period. And remember those secondary ejecta we talked about? They're not just solid rocks. Fine dust can be part of that ejecta, creating a sandblasting effect if you're in the wrong place at the wrong time. Now let's address something that's fundamentally unsettling about the Moon from a human perspective: the gravity. At 1/6 of Earth's, it's enough to keep you on the ground, but it's not enough to feel normal. Studies of astronauts in microgravity have documented numerous health effects: bone density loss, muscle atrophy, fluid shifts that affect vision, changes in cardiovascular function. The Moon's gravity is not microgravity, so some of those effects might be mitigated. But we don't actually know. No one has spent extended periods in partial gravity environments. The Apollo astronauts were only on the Moon for a few days, not long enough for significant physiological changes to occur. We're essentially guessing about what happens to the human body after weeks or months at 1/6 gravity. Some effects are likely. Bones respond to stress by maintaining or increasing density. Reduce the stress and they adapt by losing density. This happens dramatically in microgravity. It will probably happen to some degree in lunar gravity, though perhaps more slowly. Muscle atrophy is similar. Use less effort to move and your muscles adapt by getting weaker. Astronauts on the International Space Station have to exercise 2 to 3 hours per day to counteract these effects. On the Moon, exercise routines would be essential, but would they be enough? There's also the question of adaptation when returning to Earth. If you spend 6 months or a year on the Moon, your body adapts to that environment. Your bones, muscles, and cardiovascular system adjust to the lower gravity. Then you come back to Earth, and suddenly gravity is 6 times stronger. The strain on your body would be immense. Astronauts returning from long-duration stays on the International Space Station have difficulty walking, standing, even sitting up. They feel dizzy, weak. It takes weeks or months to readjust. Coming back from the Moon might be even harder because your body has partially adapted to a specific gravity level rather than zero gravity. You've maintained some bone and muscle, but not enough for Earth. The transition could be brutal. Some researchers worry about the risk of bone fractures in returning astronauts. Bones weakened by months in low gravity might not handle the sudden increase in load when returning to Earth. And here's a particularly concerning scenario. What if there's a medical emergency that requires return to Earth, but the astronaut has been on the Moon long enough that their body has weakened? The acceleration forces during launch and the multi-day journey back to Earth could be dangerous. In their weakened state, you might need to evacuate someone for medical treatment, but the evacuation itself could kill them or worsen their condition. It's a no-win situation. Let's talk about fire for a moment. On Earth, fire is a constant danger. On the Moon, fire behaves differently, and in some ways it's even more dangerous. Remember the Apollo 1 disaster? 3 astronauts died in a fire during a ground test. The spacecraft was pressurized with pure oxygen to simplify the life support system. When a spark ignited materials inside, the fire spread with terrifying speed in that oxygen-rich environment. The astronauts couldn't escape in time. Lunar habitats won't use pure oxygen. They'll use a nitrogen-oxygen mix similar to Earth's atmosphere, which is less flammable. But fire is still a major risk. If a fire starts in a sealed habitat, You can't just open the windows for ventilation. You're in a contained environment. The fire consumes oxygen and produces carbon dioxide and toxic smoke. Fire suppression systems would be essential, but they add complexity and mass. And here's the thing about fire in low gravity. Flames behave differently. On Earth, hot air rises due to buoyancy, pulling fresh oxygen into the base of the flame and carrying combustion products away. In reduced gravity, this convection is weaker. Flames can become more spherical, spreading in all directions. They can smolder in ways that make them harder to detect and extinguish. Research on the International Space Station has shown that combustion in microgravity is complex and sometimes unpredictable. Lunar gravity would be different again, and we have limited data on how fires behave in that environment. A fire in a lunar habitat would be a desperate situation. You'd have to suppress it quickly before it consumed too much oxygen or damaged critical systems. If suppression fails, you might have to evacuate to another module or shelter and seal off the affected area. But if the fire has damaged your only habitat, or if you don't have a backup, your options become extremely limited. You're in a spacesuit with a finite air supply, standing on a surface that can't support human life, waiting for rescue that might not come in time. Fire suppression systems themselves present challenges. On Earth, we often use water-based systems, sprinklers, fire hoses, but water is precious on the Moon. Using it for fire suppression means potentially losing a critical resource. Alternative systems exist: carbon dioxide flooding, which displaces oxygen and suffocates the fire. Halon or other chemical suppressants, but these systems can be dangerous to humans. If you're flooding a compartment with CO2 to extinguish a fire, anyone in that compartment is also being suffocated. The ideal scenario is preventing fires before they start. Careful material selection, using only flame-resistant or non-flammable materials in habitat construction, rigorous electrical safety standards, regular inspections. But prevention is never perfect. Equipment malfunctions, accidents happen. Human error occurs. A single moment of carelessness, a faulty wire, a spark in the wrong place, and you have a crisis that could kill everyone in the habitat. Now let's discuss something that affects every long-duration space mission, but is particularly acute on the Moon. Supply, logistics, everything you need has to be transported from Earth. Food, water, air, spare parts, medical supplies, scientific equipment. The list is endless. Each supply mission costs hundreds of millions of dollars. Launch windows, while more frequent for the Moon than for Mars, still impose scheduling constraints. If something critical runs out unexpectedly, if consumption is higher than planned, or if a resupply mission is delayed, the consequences could be dire. Imagine rationing food because the next supply shipment is delayed by technical problems. Imagine stretching medical supplies, hoping no one gets seriously injured before the next delivery. The psychological stress of watching your consumables dwindle, knowing that help might not arrive in time, would be immense. And supply missions can fail. Rockets malfunction. Spacecraft have accidents. The history of spaceflight includes numerous failed missions. Some Russian Progress cargo spacecraft bound for the International Space Station have failed to reach their destination. Launch failures. Docking failures. If a supply mission to a lunar base fails, the crew might be forced to evacuate if they can't sustain themselves until the next mission. This creates a fundamental vulnerability. The base is dependent on a long, fragile supply chain stretching 250,000 miles. Any break in that chain, any disruption to the flow of supplies, puts lives at risk. It's like living on a desert island where the supply ship comes every few months. If the ship doesn't arrive, you're in trouble. Except on this island, you can't even breathe the air or drink the water without technology. Some of this vulnerability could be reduced through in-situ resource utilization, as we discussed earlier. If you can extract water from lunar ice, you're less dependent on water shipments from Earth. If you can grow some of your own food, you're less dependent on food shipments. But achieving meaningful self-sufficiency would require extensive infrastructure. Industrial-scale ice mining operations, large greenhouse facilities, manufacturing capabilities to produce spare parts and equipment. Building all of that infrastructure requires enormous initial investment and carries its own risks. There's also a more subtle logistical challenge: waste management. On Earth, we generate waste constantly: food packaging, broken equipment, bodily waste. We dispose of it or recycle it without much thought. On the Moon, waste management becomes a critical challenge. You can't just throw things away. There's nowhere for them to go. Some waste can be recycled. Water from urine and humidity can be purified and reused, as is done on the International Space Station. Organic waste might be composted for use in growing food, though that requires careful management to avoid contamination. But some waste can't be recycled with available technology. Packaging materials, broken electronics, toxic substances. Do you store it? That requires space, and space in a lunar habitat is at a premium. Do you dispose of it on the lunar surface? That raises questions about contamination and environmental impact. Scientists are concerned about preserving the lunar environment for research. If we start littering the Moon with garbage, we might destroy the very scientific value we came to study. There's also the issue of human waste, feces, urine, all the biological outputs of human bodies. On the International Space Station, some of this is recycled, but some is stored in waste containers that are eventually loaded onto cargo spacecraft and burned up in Earth's atmosphere during re-entry. On the Moon, you don't have that disposal option. You have to process it on-site or store it indefinitely. NASA engineers have developed sophisticated waste processing systems, but they're complex, require energy, and can malfunction. If your waste processing system fails and you can't fix it quickly, conditions inside the habitat deteriorate rapidly, unpleasant at best, health-threatening at worst. And the psychological impact of living in degrading sanitary conditions while trapped in a small habitat with other people should not be underestimated. Let's talk about another aspect of human physiology that becomes problematic on the Moon: sleep. Humans evolved with a 24-hour day-night cycle, which our circadian rhythms are tuned to. The International Space Station maintains a 24-hour schedule despite orbiting Earth every 90 minutes, seeing 16 sunrises and sunsets per day. Astronauts follow Earth time with artificial lighting schedules that simulate day and night. On the Moon, the situation is more complex. The lunar day is about 29.5 Earth days. 2 weeks of continuous sunlight followed by 2 weeks of continuous darkness. Your habitat lighting could simulate a 24-hour cycle, but there's something psychologically unsettling about knowing it's been daylight outside for 10 days straight, or dark for 10 days straight. Studies on Earth have shown that circadian rhythm disruption contributes to a host of health problems: sleep disorders, mood disturbances, cognitive impairment, metabolic issues, even increased cancer risk over long periods. Astronauts on the International Space Station frequently report sleep problems despite carefully managed light schedules. The Moon, with its alien day-night cycle, might be even more disruptive. There's also the issue of light quality. Sunlight on the Moon, unfiltered by atmosphere, has different spectral characteristics than sunlight on Earth's surface. It includes more ultraviolet light, which habitat windows would have to block. The artificial lighting inside habitats would try to replicate natural sunlight, but perfect replication is difficult. Subtle differences in light quality might affect circadian rhythms, vitamin D production, and psychological well-being in ways we don't fully understand. And here's something that connects back to radiation exposure. Cosmic radiation includes particles that create flashes of light when they pass through the human eye. Astronauts traveling to the Moon during Apollo missions reported seeing these flashes even with their eyes closed. On a long-duration lunar mission, you'd experience these phantom light flashes regularly, especially during solar events when radiation levels spike. Imagine trying to sleep while your closed eyes are randomly flashing with light from cosmic rays passing through your retinas. It sounds like something from a horror story, but it's a documented phenomenon. Now let's address something that's become increasingly relevant as we contemplate permanent lunar presence: planetary protection and contamination. This works both ways. We're concerned about contaminating the Moon with Earth life, and we're concerned about bringing lunar materials back to Earth that might pose unknown risks. The forward contamination issue, Earth to Moon, might not seem like a big deal. The Moon is sterile, right? It's been bombarded by lethal radiation and exposed to vacuum for billions of years. Nothing lives there. But that's precisely why scientists want to keep it pristine. The Moon's environment is a time capsule, preserving materials and conditions from the early solar system. If we contaminate it with Earth microbes, we potentially compromise scientific research. Some microbes are incredibly hardy, extremophiles that can survive radiation, vacuum, extreme temperatures. If these organisms hitch a ride to the Moon on spacecraft or equipment, they might survive in protected microenvironments. Imagine trying to study the potential for indigenous lunar ice to contain organic compounds from the early solar system, only to discover that what you're finding is Earth contamination from your own operations. NASA has planetary protection protocols designed to minimize this risk, but sterilization has limits. You can't autoclave an entire spacecraft or habitat module. Some level of microbial contamination is inevitable when humans are involved. We carry trillions of microbes on and in our bodies. Everywhere we go, we shed bacteria, skin cells, organic material. A lunar habitat will quickly become contaminated with Earth life, and preventing that contamination from spreading to the surrounding environment is extraordinarily difficult. The back contamination issue is more speculative, but potentially more serious. What if lunar materials, especially ice from permanently shadowed craters that have been isolated for billions of years, contain something unexpected? Exotic chemistry, unknown organic compounds. The probability of finding actual living organisms on the Moon is essentially zero, but unexpected chemical or biological properties in lunar materials could pose risks. Apollo astronauts were quarantined after returning from the Moon for the first few missions. This was primarily a political and public relations measure rather than a serious scientific concern, but it acknowledged the possibility of unknown risks. As we begin returning larger quantities of lunar material to Earth, especially if we start mining operations, the question of contamination becomes more pressing. Do we need biosafety protocols, quarantine procedures? These add complexity and cost to missions. Let's talk about something more immediate and practical: tools and equipment. Working on the Moon requires specialized tools designed for use in vacuum, extreme temperatures, and while wearing pressurized gloves. This is harder than it sounds. Try doing delicate mechanical work wearing thick gloves. Try operating a power drill when your gloves reduce your sense of touch to almost nothing. Try reading small print on a display when your helmet is fogged up or coated with dust. Apollo astronauts struggled with these issues during their limited time on the surface. Simple tasks that would take minutes on Earth took much longer in spacesuits. Fatigue from working in a pressurized suit was significant. On longer missions, where extensive construction, maintenance, and repair work is necessary, these difficulties multiply. Every task takes longer, requires more effort, and increases the risk of mistakes. Glove design is particularly challenging. You need enough dexterity to manipulate tools and perform fine motor tasks, but you also need protection from the vacuum, temperature extremes, and the sharp, abrasive lunar dust. Current spacesuit gloves are a compromise that doesn't fully satisfy either requirement. Astronauts frequently report hand fatigue and even injury from working in pressurized gloves for extended periods. The constant effort of gripping against the pressure of the glove causes soreness and can damage fingernails. The sense of smell is also affected. Inside a spacesuit, you smell only yourself, and the interior of the suit, which astronauts have described as having a distinctive, not particularly pleasant odor. Inside the habitat, smells become intensified because of the closed environment. Any cooking odors, body odors, chemical smells from equipment linger. There's no fresh air to ventilate them away. Air filtration systems work constantly, but they can't completely eliminate odors. Interestingly, lunar dust has its own distinctive smell. Apollo astronauts reported that when they brought lunar dust into their spacecraft after it had been exposed to the cabin atmosphere, it smelled like spent gunpowder. This is likely due to chemical reactions between the reactive dust particles and oxygen and moisture in the air. It's a sharp, acrid smell that many astronauts found unpleasant. On a lunar base, that smell would be a constant companion, a reminder that you're living in an alien environment. Touch is complicated by the need to wear protective equipment. You never directly touch the lunar surface. It's always filtered through glove material. You never feel lunar wind on your skin because there is no wind. Temperature sensations are mediated by your suit's climate control. You're physically present on the moon, but in many ways you're isolated from it, experiencing it through technological barriers. This sensory disconnection might contribute to feelings of unreality or detachment. Astronauts sometimes describe feeling like they're in a simulation or a dream. The sensory experience is so different from Earth that it doesn't feel quite real. This dissociative effect, combined with isolation and stress, could affect mental health in unpredictable ways. Now let's address something practical but often overlooked: clothing and personal items. On a short Apollo mission, astronauts could manage with limited clothing, but on a months-long mission, personal hygiene and comfort become important for both health and morale. Yet mass restrictions mean you can't bring extensive wardrobes. Clothing has to be worn multiple times. Washing facilities are limited because water is precious. The International Space Station has some capacity for washing clothes, but it's limited. Often clothing is worn until it's too dirty, then disposed of as waste. On the Moon, the same approach might be necessary, but disposing of waste is problematic, as we discussed. Recycling textiles is possible, but requires equipment and energy. The result is that crew members might spend months wearing a limited selection of increasingly worn clothing, which doesn't contribute to psychological well-being. Personal items are similarly limited: photographs, books, music, small mementos. These things matter psychologically, helping people maintain connections to home and sense of personal identity. But every item has mass that has to be justified. There's a calculation of psychological value versus physical cost for every personal item someone brings to the Moon. Modern technology helps. Digital photographs don't have mass. E-books and streaming media provide virtually unlimited entertainment options without physical weight. But there's something about physical objects, tangible items you can hold, that matters psychologically. A printed photograph feels different than a digital image on a screen. The limitations on personal items might seem trivial compared to the physical dangers, but they contribute to the overall psychological burden. Let's talk about time perception. Living on the Moon would fundamentally alter your sense of time. The day-night cycle is wrong. Earth's phases in the sky don't match your internal calendar. Communications with Earth have delays. You're living on a different world, operating on schedules that are dictated by operational needs rather than natural rhythms. There's also the temporal disconnection from Earth life. Events happen back home. Friends and family experience life changes. The world moves on while you're isolated on the Moon. You follow these events through communications, through video calls with delayed transmissions, but you're not part of them. You're an observer of Earth life rather than a participant. This temporal and social disconnection is something long-duration space travelers have to cope with. Astronauts on the International Space Station experience it to some degree, though they're much closer to Earth and can return relatively quickly if needed. On the Moon, the disconnection is more profound. The journey back takes days. You're truly separated in a way that few humans have ever experienced. Some psychological research suggests that maintaining routines helps people cope with extreme environments. Regular schedules, consistent meal times, exercise routines, traditions and celebrations. Lunar base operations would try to incorporate these stabilizing elements, celebrating birthdays, marking holidays, maintaining as much normalcy as possible within the constraints of the environment. But there's a tension between the routine needed for psychological stability and the monotony that routine creates. Doing the same tasks every day, seeing the same people, living in the same limited spaces. The sameness can be psychologically wearing. You need routine, but too much routine becomes soul-crushing. Balancing this is a delicate task for mission planners and crew members. Now let's discuss something that connects to the very infrastructure of a lunar base. Communications and data systems. Everything depends on computers and networks functioning reliably. Life support monitoring. Navigation systems. Scientific equipment. Communications with Earth. Entertainment and psychological support. If your computer systems fail or are compromised, you're in serious trouble. The lunar environment is hard on electronics. Radiation can cause bit flips in computer memory, where cosmic rays strike chips and change data. Shielding helps, but doesn't eliminate the problem. Systems need error checking and redundancy to detect and correct these errors. Temperature extremes, stress components, dust can infiltrate even well-sealed electronics over time, causing shorts and failures. There's also the question of cybersecurity. A lunar base would be a high-value target for various kinds of cyber attacks. Nation-states might want to spy on operations or demonstrate capability. Terrorist groups might see a lunar base as a symbolic target. Even non-malicious hackers might try to penetrate systems just to prove they can. The consequences of a successful cyber attack on a lunar base could be severe. Disrupted communications, compromised life support systems, corrupted data. Defending against cyber threats while operating at lunar distances is challenging. Security updates and patches from Earth take time to transmit and implement. If a zero-day vulnerability is discovered in critical systems, there might be a window of exposure before fixes can be deployed. And the isolation of a lunar base means that incident response capabilities are limited. You don't have cybersecurity teams on site. You're dependent on remote support from Earth with communication delays. Let's talk about something even more fundamental: energy. Everything on a lunar base requires power. Life support, heating and cooling, communications, scientific equipment, manufacturing, lighting. The power demands are substantial, and power generation on the Moon has significant challenges. Solar power is the obvious choice. The Moon gets abundant sunlight during the lunar day, but the 2-week night means solar panels alone can't provide continuous power. You need energy storage. Batteries are the standard solution, but they add mass and have limited lifespans, especially in the harsh lunar environment. Advanced battery technologies are improving, but storing 2 weeks' worth of energy for an entire base requires enormous battery capacity. Some proposals suggest nuclear power as an alternative or supplement. Small nuclear reactors could provide steady power regardless of day-night cycles. But nuclear systems come with their own challenges, safety concerns, regulatory hurdles, the need for specialized expertise to operate and maintain them, heat rejection, since you can't use convective cooling in vacuum, and the political and public relations challenges of putting nuclear reactors on the Moon. There's also the possibility of locating bases in permanently sunlit regions. like the peaks of certain craters near the poles. These locations receive nearly continuous sunlight, solving the energy storage problem. But they're also among the most difficult terrain to access and build on, and they're far from the permanently shadowed regions where water ice exists, which is a resource you want close access to. Power distribution is another challenge. Running cables across the lunar surface to connect different facilities exposes them to the harsh environment. Thermal cycling, micrometeorite impacts, dust abrasion. Underground cables would be protected but require excavation, which is difficult on the Moon. Wireless power transmission is theoretically possible but has efficiency losses and technological challenges. If power generation or distribution fails, the consequences cascade rapidly. Life support systems run on backup power, but backups are limited. Hours, maybe a couple of days at most. Then you're in an emergency situation requiring evacuation or desperate repair efforts. Energy is the foundation everything else rests on, and ensuring reliable power in the lunar environment is one of the most critical engineering challenges. Now let's address something we've circled around throughout this discussion: the human cost. Not just the risk to individuals who choose to go, but the broader human cost of lunar exploration. The resources devoted to this endeavor could be used for other purposes. The brilliant minds working on lunar base engineering could be working on climate change, disease, poverty, education. The hundreds of billions of dollars could fund countless initiatives on Earth. This is the classic debate about space exploration priorities. Supporters argue that space exploration advances technology with broader applications, inspires people, expands human knowledge, and works toward long-term species survival. Critics argue that it's a vanity project for wealthy nations, that the money would be better spent on urgent terrestrial problems, that the benefits are speculative while the needs on Earth are immediate and concrete. There's truth in both perspectives. Space exploration has indeed led to technological spin-offs and inspired generations, but it's also true that massive resources are being devoted to it while people on Earth lack basic necessities. The ethical calculation is complex and depends on how you value different outcomes, how you weigh present needs against potential future benefits, and what vision you have for humanity's future. For the people who go to the Moon, who risk their lives in that endeavor, these philosophical debates might feel distant from their daily reality. They're there because they believe in the mission, because they're driven by curiosity and ambition, because they want to be part of something larger than themselves. But the sacrifices they make, the risks they accept, are real and personal. And if something goes wrong, if people die on the Moon, society will have to grapple with whether those sacrifices were justified. The Moon is magnificent in its desolation, terrifying in its hostility, and fascinating in its alienness. It's a place that calls to something deep in human nature, the drive to explore, to go beyond the known, to test ourselves against the ultimate frontier. But it's also a place that could kill you in countless ways, quickly or slowly, obviously, or subtly. Living there would require accepting risks that most people would find unacceptable, enduring hardships that would break many, and maintaining psychological resilience in the face of constant stress and danger. The people who choose to go anyway, who train for years, who say goodbye to loved ones knowing they might not return, who step onto that grey, dusty, airless surface and call it home for months or years. Those people are either remarkably brave or slightly mad, probably both. They're the pioneers who will teach us whether humans can really live beyond Earth, whether we can adapt to worlds that were never meant for us, whether our species has a future among the stars, or whether Earth is and will always be our only true home. And if you think living on the Moon sounds challenging, wait until you hear about the nightmare of trying to survive on Mars. If you want to understand the full scope of what interplanetary colonization would really demand, I invite you to watch the video on the screen. See you there.